An equivalence relation is a subset of the Cartesian product of a set with itself. So let's say we're given a set X. An equivalence relation E on X is a subset of the Cartesian product of X with itself. But it's not just any subset, it's a subset that has special properties. First of all, it has the property of reflexivity, which means that for every X in the set X, the pair XX must be an element of E. An equivalence relation must also be symmetric, which means that for any two elements X and Y in X, if the ordered pair XY is in E, then the ordered pair YX must also be in E. And finally, an equivalence relation must be transitive, which means for any elements X, Y, and Z in X, if the ordered pair XY is in E, and also at the same time the ordered pair YZ is in E, then this should imply that the ordered pair XZ is also in E. So an equivalence relation E on a set X is a subset of the Cartesian product, such that the properties of reflexivity, symmetry, and transitivity hold. But what does all of that mean intuitively? Let's say our set X is the set of objects, two triangles, and two squares. An equivalence relation is the idea of similarity or equivalence of objects in a set. In this case, for instance, we might want to consider an equivalence relation that recognizes that the triangles are similar to each other and the squares are similar to each other. The way we can encode this information is to make a list of ordered pairs of all the objects that are equivalent to all the other objects. So in this case, our E will be the set of ordered pairs consisting of the first triangle and the second one, as well as the second triangle and the first one, which must be there due to the property of symmetry, also of the triangle in itself for each of the two triangles, which must be there. These ordered pairs must be there because of the property of reflexivity. And then the same way, similar ordered pairs will be formed from the squares. So we will have the small square and the big square and the small square, and the small square with itself, as well as the big square with itself. So the idea is that when an ordered pair XY is an element of E, X and Y are similar to each other in a certain way. In the case we're considering here, X could be one of the triangles and Y could be one of the triangles as well because they're similar. They're similar shape. Then X could be a square and Y could be a square as well because the squares are similar as well. But we can't have X to be a triangle and Y to be a square because the triangle and the square are not similar. However, there could be another equivalence relation where the triangle and the square do get to be grouped together. Here is an example. Let's extend our set X with further elements. Let's say, apart from these shapes, we also have an apple and glasses. The new equivalence relation we'll consider in this set will identify that these four objects are all shapes and hence they're similar to each other. Apple will only be similar to itself and the glasses will also be only similar to itself. So in this new example, we will have elements such as the triangle and the square and the triangle, and so on, grouping any two shapes together, including the same one, because of reflexivity. As for the apple, it will only group with itself in an ordered pair, as well as the glasses. The glasses will only come with itself in an ordered pair. Here is yet another example of an equivalence relation. Consider the set X to be the set of all natural numbers, including the number 0. Define E to be consisting of those ordered pairs X and Y, where Y equals 2 times X. At this stage, we can't be certain that this E is a subset of X cross X, because potentially X could be a negative number, and then Y will be 2 times that. Such a pair will not be element of X cross X, because X cross X will only contain pairs where both the first and the second coordinate are natural numbers. So, we have to slightly adjust this notation to ensure that E is a subset of X cross X. We can do this as follows. In this new notation, we are only considering those X and Y that come from capital X and capital X respectively, so we're only considering the natural numbers X and Y. There is another problem, however, with this example. This relation is not an equivalence relation. There are actually several problems with it being an equivalence relation. In fact, none of the properties of reflexivity, symmetry, or transitivity hold here. For example, the pair 1, 1 is not an element of E. How can we see this? Well, if it were an element of E, Y should be equal to 2 times X. This relation is not symmetric either, because while 1, 2 is an element of E, indeed, since 2 times 1 does equal to 2, 2, 1, which should have been an element of E by symmetry, isn't there, because 2 times 2 does not equal to 1. Notice that the right-hand side here represents the Y value in the formula, whereas the left-hand side is the right-hand side of the equation there. Neither is this relation transitive. Why isn't it? While 1, 2 is in E, as we have already confirmed, and for similar reasons, 2, 4 is in E as well, because 4 equals 2 times 2, one 4 isn't in E. Rather, these two things being in E does not imply 1, 4 being in E. Hence, transitivity breaks. If transitivity were to be satisfied, 1, 2 and 2, 4 being there should result in 1, 4 to be in E as well. So this relation is not an equivalence relation, but we can easily fix it so that it becomes one. Instead of requiring that Y equals 2 times X, let's require that 2 divides Y minus X. Then the resulting relation is an equivalence relation. We can confirm this easily by checking all the 3 properties. Is it true that X is always in E? Well, that would be true if it were true that 2 divides x minus x. X minus x is 0, and of course 2 divides 0. If xy is in E, then 2 divides y minus x, but then also it divides x minus y, which then results, by this rule of how we select the ordered pairs in E, that yx is also in E. This confirms symmetry of E. What about transitivity? Well, if xy is in E and yz is in E, this implies that 2 divides y minus x as well as z minus y. If 2 divides both of these numbers, then 2 will also divide their sum. Now the sum of z minus y and y minus x is precisely z minus x. And the fact that 2 divides z minus x implies, by definition of E, that the pair xz is in E as well. And that's exactly what transitivity requires. If xy is in E and yz is in E, then xz, the ordered pair xz, must also be in E, which we have now confirmed. We said earlier that an equivalence relation is supposed to capture the idea of similarity of objects. Which similarity does this equivalence relation capture? To answer that question, let's list a few examples of elements of E. 0, 2. Is it in E? 2 minus 0 is 2. And certainly 2 does divide 2. 0, 2 indeed is in E. What about 1, 2? In order for 1, 2 to be in E, 2 must divide, remember the rule, y minus x, where y is the second coordinate and x is the first coordinate. Our y is 2, our x is 1. Y minus x will be 2 minus 1, which is 1. But of course, 2 does not divide 1. So, 1, 2 is not in E. 0, 2 is in E, however, as we established. And of course, 0, 4 is also in E. 2, 4 is also in E. What about 1, 3? 1, 3 is in E because 2 does indeed divide 3 minus 1, which is 2. By listing more and more examples of elements of E, we soon start to notice that an ordered pair xy will be in E when either both x and y are even, as it happens in this case, in this case, and in this case, or when both x and y are odd, as it happens in this case, for instance, but does not happen in this case where one of them is even and the other is odd. So this equivalence relation groups together the even numbers and the odd numbers. All the even numbers are similar to each other according to this relation, and all the odd numbers are similar to each other, but no even number is similar to odd by this equivalence relation. The picture I drew here is actually a picture for a related concept of a partition. That's when you take a set and you divide it into disjoint blocks. But that's for a different video.